So good afternoon, everyone. It's a pleasure to have you all here. My name is Jared Woloszewski.
My name is Mitch McDermott.
Colin Howard.
I'm Alex Anthony.
And this is our project, Instrumentation and Validation of the Formula FSAE vehicle. First, we'd like to thank our company sponsor, James Bossard at Corporation, and our faculty advisor, Dr. Gattasala. Their support helped us complete this project.
So a little background information on what Formula FSAE is. It's an international collegiate competition where teams worldwide will compete by creating and designing a Formula-style race car. We usually all meet annually at MIS to compete in dynamic and static events varying from design presentations to actual time races. Western Michigan's average schedule is usually throughout the fall semester. We design a new vehicle every year. And then going into the spring semester, we'll actually manufacture and test that vehicle. Following the summer, we'll begin racing and preparing for the international competition as stated before. So as the production timeline for these vehicles is roughly one school year, we rely heavily on pre-calculated load cases to design our vehicle around. In order to fully validate those pre-calculated load cases, our project was to fully instrument the previous year's Formula FSAE vehicle. Using the instrumentation and data collected on live track data and the chassis dyno, we were actually able to create new benchmarks for subsystem that's in Navity and also adjust and adapt benchmarks that we currently design.
So our project is split into three sections. The first section is powertrain stress analysis, where the biaxial state of stress was measured on both the engine and differential mounts. Our second section is powertrain performance analysis, where the critical systems of our powertrain were analyzed doing dyno and track testing. Our final section of our report is suspension position and validation, where track testing was performed in order to ensure that the suspension was working as intended, as well as creating new benchmarks and design constraints.
So most of our general data collection setup was used through a 16-channel Eaton track box, which was also controlled by a custom LabVIEW program, which is supplied by Eaton called Yeti. The Yeti software would control all the data collection in the process, with live data analysis that can be viewed while on the track, along with providing custom calibration tables for every instrument that was used. You can see that in the center, you can see the depicted track box as well as it open on the upper coating. We also used multiple data port signal conditioners for each instrument that was collected during this project. These signal conditioners were used because they could provide the appropriate excitation and amplification for all the instruments that were used during the data collection.
On the vehicle side of things, it's equipped with a link Fearing engine control unit. The ECU comes with 512 megabytes of onboard data logging. This was used to log selected sensor data that is already connected to the vehicle, not in the DAC box. So certain control conditions can be set up. For instance, in the far right image, it shows 1,000 RPM. So as soon as 1,000 RPM is attained, the data logging will start. However, in order to make this work with the DAC box, we set another condition of sending 5 volts from the DAC box to the ECU. As soon as that signal is received, the ECU will begin recording at the same time the DAC box did to make sure everything is recording at the same rate.
So in order to secure the Triton box during testing, a mounting system was designed using SolidWorks. As you can see in the top right, 2 mounts were purchased from Summit Racing, while the front 2 mounts were designed and 3D printed. During track testing, the laptop used to record data was also needed to be attached to the chassis and vehicle itself. So a hard shell laptop case was purchased and attached to the top of the Triton box in order to secure it during track testing.
So we conducted some dynamometer testing on the DynoJet eddy current dynamometer here at Western. So it comes equipped with PowerCore software and WinPep 8 software. The PowerCore software is shown in the top right. And to read RPM, there is an inductive pickup that is installed onto the wire to the coil pack. Every time the spark plug pulses, it sends a signal which reads the RPM. Then the power and torque curves are output to WinPep 8 software, which will be shown later on. Some various things we did on the dynamometer. We did some power pulls from 0 to 14,500 RPM, as well as some steady state analysis using the dyno's load control feature. So this was done at about 6,000 steady state, 9,000, and 11,000.
Eaton's Marshall Proving Grounds were used to conduct on-track testing. 5 courses were set up to simulate competition events. First being acceleration, the car will accelerate a straight line for 75 meters. Braking event, the car will accelerate, lock all 4 wheels, and be required to stop in a certain braking area. skid pad, which is one of the 4 main competition events where the car will drive in a figure-8 pattern. Slalom and then quartering setups, including a hairpin and tight turn, set up to mimic autocross and endurance events at competition. Those events are 2 of the longer events, so we did not have any space to set up those events.
So to ensure the vehicle was at its peak condition for testing, some routine maintenance was completed. So some of the routine maintenance included replacing powertrain fluids such as the oil, the coolant, as well as inspecting and tightening the chain. Also for suspension, the toe was set as well as the camber, and then it was corner weighting to make sure that the vehicle was balanced. Following the initial stages of testing, there was a transmission failure with the engine, and it is built into the engine in this case. Therefore, we had to do a transmission swap, which a rough image is shown on the right there. And then while doing the rebuild, we also inspected the valves, as during a compression and leak down test, the compressor was very low. So we did some valve maintenance as well, which is just a picture to highlight that there.
Most of the instrumentation used in this project was provided by Eden, but additionally we received 2 undergraduate research awards that provided funding for infrared temperature sensors, brake pad thermocouples, and a new set of racing tires for on-track testing. The rest of the budget was used from the Formula FSAE team to purchase additional requirements.
So the timeline was as follows. We had general vehicle preparation, and then chassis dynamometer instrumentation setup and calibration. Then came the dynamometer testing, along with the analysis that came after we acquired the data. Then the next section was dynamic track testing, so the instrumentation was set up and calibrated for that. And then vehicle track setup and tuning for the vehicle was done again, and then followed finally by the dynamic track data collection and analysis.
So to start our powertrain stress analysis, we're going to begin with the engine notes. So as the chassis highly utilizes the rigidity of the engine block to increase its torsional rigidity, these mounts are extremely crucial to the actual frame itself. To validate the stress that was actually seen through each engine mount, biaxial strain gauges were geared onto the mounts in the longitudinal and latitudinal direction. These strain gauges were read individually using a custom Wheatstone bridge adapter, as one gauge represents only one leg of the Wheatstone bridge, so 3 actual resistors were used to create a full bridge unit that the DAC system could actually understand. So previously in the design, the Formula FSAE team considered the engine stress to be negligible. As it was found through our actual runs depicted in this table below, the stress was actually not negligible, as it was found using the directions for each gauge in the longitudinal and longitudinal direction. There's actually a moment applied on the rear subframe from the stress of the engine block run. From the data collected, factors of safety were calculated for each mount using the yield strength of 4130 chromoly, which is what the rear subframe is made of. It was found that the lowest factor of safety was a 1.15 on the rear left mount, which makes sense as it's right above the output shaft of the motor. As that factor of safety is quite low, we advise the team to increase the thickness of the rear structure to hopefully improve that and avoid catastrophic failure in the future.
So a differential is a mechanism that links 2 rear axles together so that when a vehicle undergoes a turn, the inside wheel can rotate at a slower rate than the outside wheel, preventing any skidding. So in order to position the differential between the 2 axles, 7075 T6 aluminum mounts were designed using SolidWorks. In order to avoid catastrophic failure, if the mounts were to fail, they were also simulated using SolidWorks static simulation, and we found a factor of safety of around 2.54. In order to record the actual stress for this testing, we used rectangular rosette strain gauges and placed them on the 4 locations shown here near the chassis. These measure the biaxial state of stress at unknown principal directions. And the way that these work is they measure the stress in the 0, 45, and negative 45 directions shown on the bottom left. So we recorded data during our dyno runs and was analyzed using Excel. From this data, we took the max stress at each different location. For example, BL would stand for bottom left, and at the 3, 0, 45, and negative 45 directions as well. From that, the maximum strain was calculated using this equation here, and the average principal direction was calculated using this equation. As you can see, the average principal direction has notation, meaning, looking at this picture here, you can see the notation used for rosette strain gauge. Similarly to the engine mounts, factor of safety was calculated using the maximum stress and yield strength of 7075 T6 aluminum. From this, you can see that our minimum factor of safeties are normally around the 0 direction, and our minimum being 2.66. This was higher than our simulated result of 2.54. Due to maintenance and other time constraints, we had not planned to originally do launch testing for a differential mounting system. Luckily, we were able to get some launch testing in with the one remaining strain gauge that was still operational. This was for the top left strain gauge shown here. This data was used to calculate a percentage change between normal and launch testing, which, as you can see here, increased in launching. The principal direction also changed, and you can see here the new factor of safety values using a very rough estimate by applying the percentage change to the other 3 locations. From this data, you can see that the minimum is now 2.11, which is lower than our estimated factor of safety of 2.54, but still greater than our goal of greater than 2.
WMU's FSAE vehicle is powered by a 2007 Honda CBR 600R engine. Due to FSAE rules, we are limited to 710 cc of displacement, and an air restriction must be applied, which is about 19 to 20 millimeters, dependent on fuel choice. So it's imperative for us to generate as much power as we possibly can. So we did some dyno testing before the engine rebuild and after the engine rebuild. So before the engine rebuild, you can see in the table, we generated about 69 horsepower at 11,000 RPM and about 35 foot-pounds of torque at 9,000 RPM. Following the rebuild, we generated 77 horsepower at 12,000 RPM, as well as 50 foot-pounds at 8,000 RPM. So we had an increase of about 7 horsepower and 15 foot-pounds just from the belt maintenance and engine rebuild. Some of the power pools can be shown there, and then we did some steady state analysis as well. So the cooling system on the FSAE vehicle is equipped with a Davies-Craig electric water pump, a Mishimoto aluminum radiator, as well as aluminum part lines. And it is they already have pre-existing thermocouples installed in the engine exit, as well as the radiator exit to record water temperatures. So to add to the project, we installed Type K thermocouples in the air inlet and air exit of the radiator as well to give us further cooling analysis. So in the past, the vehicle's cooling system was not analyzed much. There is not much recorded data on this, so it's something we wanted to look into. So here we have 2 minutes of data collected during on-track testing, which was used to calculate how much heat was dissipated by the radiator. So the initial equation here, which relies on the mass flow rate of the water, the specific heat at constant pressure, and the temperature delta between inlet and exit of water temperatures. So this was used to find that the heat dissipated by the radiator was 23.8 kilowatts. And then to follow up on that in some simulations that the team uses already, we use Lovik's empirical correlation because it contains values that we already know, such as vehicle displacement, volume, the torque, the power, and the engine RPM. So using that equation, we find that the engine dissipates about 24.17 kilowatts to the coolant. Therefore, at about a negative 1% of performance. So we are underperforming, which aligns with the findings that we have during longer events such as endurance. The engine tends to overheat. Also, this 1.5% comes with the assumption that we have maximum flow rate generated by the water pump, which is also usually not the case. Therefore, we should really look into redesigning the cooling system so it's more effective.
So, oiling system in a vehicle is responsible for reducing the friction between moving parts by lubricating it with oil. And since 2018, the Formula SA team has utilized a dry sump oiling system. The dry sump oiling system works by storing all the oil in an external reservoir and therefore it's not being stored in the actual oil pan itself. This allows us to lower the engine and reduce weight center of gravity. So the dry sump oiling system further works by storing the oil in the reservoir, as I talked about. While it's stored in the reservoir, this gives the oil the opportunity to de-aerate and cool. The cooling in the reservoir allows us to not need any alternative oil cooling system for our vehicle. So what we were trying to do for this testing was determine the temperature difference that the reservoir is cooling the oil during operations. And by doing this, we installed a Type K thermocouple into the fan fitting of the inlet shown here. And we utilized an already installed Davies temperature sensor that was installed in the bottom of the reservoir there. So data was taken during dyno testing and was shown here in this bottom left. We recorded the minimum and maximum temperature differences, and we found that the minimum temperature difference is around 27.62 degrees Celsius with a maximum of around 27.74. Although there were no prior benchmarks for our team, this value was much higher than we expected.
The current vehicle's exhaust system can be observed here. It is a 4-to-1 system with equal length runners about 14.5 inches long. So a process that was kind of developed and should be used for tuning is shown here. We drilled out 4 holes, 1 in each runner, about equivalent distance from the exit of the cylinder. And then weld bungs were welded to them, where thermocouples can then be threaded into the exhaust runners. These EGTs are then a useful tool for engine tuning. For instance, you can compare your air-fuel ratio with your various temperatures to learn if you're running the engine too rich or too lean. It's also a good indication when tuning up changes that you make while tuning. So the exhaust gas temperatures versus time were plotted from a steady state run at 11,000 RPM, and they're shown here. So you can observe that runner 4 is consistently slightly higher temperature than the other 3 runners. This may lead to the assumption that you could enrich the cylinder to bring the temperatures to be more balanced. However, overall, the EGTs are within 30 degrees Celsius, which usually our target is about 100 degrees, so they're pretty well balanced. And that can be shown here as well, and as well as the maximum temperature was about 784 degrees Celsius. So this method should be used for future tuning on future vehicles. This is kind of a benchmark for that.
So moving on to suspension analysis, linear potentiometers were used to collect suspension position data. The potentiometer is a direct voltage pass-through instrument, meaning the input voltage is the same as the output voltage. As the potentiometer will compress, resistance increases, the voltage will decrease to 0. So when it was wired to the back box, it was sent a voltage of 5 volts, meaning at full extension, it will read 5 volts, and at full compression, it reads 0 volts. A conversion factor of 6 was applied to this to convert from voltage to position due to the 30 millimeters of travel. 3D printed mounting, shown in both pictures, was designed in SolidWorks to align the potentiometer in line with the shock. It's important. Potentiometer position is important to eliminate any geometric factors that need to be accounted for during calculations. So acceleration testing was performed with and without an aerodynamic package, allowing us to compare results and calculate the downforce from our package. With aero, we saw a maximum longitudinal acceleration of 0.87 Gs. This was collected using the accelerometer set up on the car, a 13% difference from our 1 G design value. Additionally, you can see in the table down here, maximum and minimum values for shock displacement. The maximum values are shock expansion, where the minimum will be shock compression. This will be useful in tuning of the suspension and adjusting the stiffness of each shock. So the same acceleration tests were completed without aero package. This allowed us to compare packages and calculate the downforce produced by both the front and rear wing. Now, the aero package is designed around downforce produced at 50 miles per hour. Now, as seen from our testing, the purple line is our wheel speed. We rarely see speeds of 50 miles an hour on short track events. So this design approach should be reevaluated by the team in order to produce better downforce numbers at lower speeds. We use the displacement difference on the front and rear shocks in order to calculate the downforce, accounting for the weight of the package by subtracting the shock displacement from with aero, without aero at steady state position. Then using our shock displacement, our spring stiffness, as well as the motion ratio of the suspension, we can calculate the downforce of the package. We produce about 48 pounds of downforce, which is about 17% difference in the front wing, and about 35 pounds of difference or 35 pounds of downforce on the rear wing, and only about a 50% difference. So we're losing a lot of downforce through the manufacturing methods from our design values. Now, skid pad, which is one of the main 4 events, is set up. The driver will enter the skid pad, do 2 laps in constant right-hand turn, and then do 2 laps in the constant left-hand turn. So this will be position data that's useful for tuning the suspension during the event. And the data we collected actually correlates to vehicle performance. So you'll notice that as the driver enters the constant right-hand turn, the right side of the car, those dampers will expand and the left side will compress due to leveling out and stabilizing of the car. And as it enters the left-hand turn, the car acts in opposite, where the left side will expand and the right side will compress. This would be very useful in adjusting stiffness of our suspension, as well as adjusting ride height based on driver feedback during skid pad. One of the main components of the suspension system is your anti-roll bar. Its main purpose is to reduce body roll during cornering. It can aid as a tuning. It's a tuning aid to adjust the stiffness of the suspension. It is designed around the roll gradient, which is the amount of body roll you have per degrees of body roll per G. It's designed around, or it's a function of torque produced by the two motor arms along the torsion bar of the A or B. So we use two torque strain gauges aligned in series to measure the torque produced by the moment bar, and we saw about a torque of 222 newton meters, about 12% difference from our design value. The loss of torque is most likely due to compliance in the suspension system. We're losing stiffness as the car is cornering, and this is something that we had previously known about, and this further validates the need for improvement of the anti-roll system.
Our current pedal box is designed around a worst case load applied to each pedal base of the throttle and the brake. To verify this load, we actually installed an Omega pancake load cell on each pedal base, which was held by a custom 3D printer seen here on the right. The data was then collected during all on-track data to see when the largest force was applied and how much that force was. From the data, it was found that the pedal reached its maximum force applied during an acceleration and the maximum force during a braking event, as you would suspect. It was also found that both pedals are designed around a 1.5 G braking load, which is where we get the anticipated force of 445 newtons. It was reported live that the throttle pedal only actually hit 28 newtons, and the brake pedal only hit roughly 78 newtons. That is a variation between 90 and 80% of the design load that's paid. This shows that the pedal box currently is extremely overbuilt and can be reduced, making it less complex and much lighter. Moving on to our brake rotors, we were validating our rotor and pad temperature by installing an embedded brake thermocouple into the pad, seen here. It was actually drilled and prepped, and then the thermocouple was pressed into the brake pad. It is a friction thermocouple, so the thermocouple will last the whole longevity of the brake. The data collected was used to validate the previous design, which you can see up here, which is used with solid simulation, as well as to see our current brake bias and how the vehicle is performing. So during a braking event, we monitor our tire temperatures, and we found that as your braking temperature increased, your stopping temperature decreased, as you can see depicted in this chart here for our 5 runs. This shows that our braking performance was doing the appropriate job that it was designed around, and was in fact working in the application we need. It was also found that the maximum temperature was 85.6 degrees Celsius, compared to the anticipated rotor temperature of 108 degrees Celsius, which is roughly a 20% difference. Now, this could be due to the fact that SolidWorks doesn't incorporate the airflow throughout the rotor during the testing or other things that the simulation doesn't truly understand. We also found, as depicted in this graph, that your rear brakes reached a much higher temperature than your front brakes, resulting in a very rear biased vehicle, which now can be known to help tune the vehicle per driver request in the future.
Tires are one of the most important components of the vehicle. Monitoring the tire temperatures is essential to the tuning of the suspension, and as your tire will heat up, grip improves, leading to faster and more efficient vehicle performance. Current Formula FSAE vehicle utilizes Hoosier racing tires that have a peak operating temperature between 120 and 140 degrees Fahrenheit. So infrared temperature sensors were installed on the vehicle to monitor tire temps while driving. Mounting was created out of 4130 steel to mount the sensor 4 inches above the tire, creating a 2.5-inch diameter circle gradient. So during the braking event, where 5 runs were completed, car showed improvement over each 5 braking runs. It was concluded that as tire temperature increased, your braking distance decreased, meaning as your tires are heating up, your grip's improving, and your stopping distance is slowing. Same result as the brake rotors had. We reached the maximum operating temperature of 153 degrees Fahrenheit, slightly above the operating temperature of the tire. This data will be very useful for future tuning of the suspension, as well as monitoring tire usage during competitions. Now, auto-cost track components, including slalom and hairpin, were constructed to monitor tire temps. From the data, it was seen that the rear tires of the car were heating up much higher than the front tires. This correlates to driver feedback, as we were seeing that the car was understeering, so the driver had to oversteer the car to compensate. and that's the result of the rear tires, or resulting in the rear tires swinging up more than the front tires. This also correlates to the same analysis that we performed with the aero analysis, where the front wing was making more downforce than the rear wing, compensating for the understeer power.
So, by completing this project, our team has new and updated benchmarks and design constraints. Certain components, such as the aerodynamic package and pedal box, can be redesigned using the new data. And other systems, such as suspension, were validated and provided with valuable information used to increase tuning and driving performance. We ran into many limitations along the way, including snowy weather, which prevented us from going and getting track data and having to reschedule, as well as damage with faulty instrumentation and an engine rebuild discussed earlier in the slides. Here's a list of all the references we used in our presentation and report.
And I'll take any questions that you guys may have.
Okay, we'll be taking questions from audience. I think there's one.
Yeah, so when you're talking about the stress on the engine mounts and the and there's also a bunch of safety factors that are screen mounts being redesigned to a optimized safety factor. That's it.
So I would say you could create individual custom engine mounts, but then in the fact where one does fail, all the stress will then go on to the other ones. But with that motor being produced, and it will actually cause all of them to fail. It's also much simpler with VR3 to give them a standard size that they can hit for all of them. I do agree that the front and rear can differ from the rear, but be customized to slightly thicker in the front, as most of the stress is seen in the rear. So I don't think it's basically.
Okay, can you get any other questions?
Yeah, I just wanted to make some comment. This is one of the very, very comprehensive projects. As we see there design with the state, you absolutely need, most of them what happens is so many sensors, so much of data, and by the time it comes to the end of the project time, you will not have enough time to complete the analysis and to get all the data. And so what I'm feeling very happy about is you guys have looked at the data and tried to analyze each part in a nice way. And the third thing is actually typically senior design projects end up around the stage. But your report is which is equivalent to a master thesis, in terms of total content availability, information. Well done, guys.
Thank you.
Any other questions we can get? All right, yeah, thanks for the good presentation and then also for the family member. Thank you, Conductor here.